So we are going to start going over section 6.1, which is the definition of an nth root. So we know a lot about square roots. Then there's a cube root, a fourth root, a fifth root, a sixth root. It goes all the way up in through infinity, potentially. Okay, that's what an nth root refers to. Can be any, the n refers to any root. So we've been talking mostly about square roots. And so we all know that if you take b, okay, that it's the square root of a if b squared is equal to a. All right. So there are a couple things to know. All positive real numbers have two real valued square roots, one positive and one negative. 0 has only one square root, which is 0, and a negative number has no real valued square roots. So that's our definition of a square root. All right, so let's put that into play here. And so if we identify the square roots of these real numbers, so for 25, we know that it's 5 and negative 5. We can square both of those numbers and they give us 25. For 16, it would be 4 and negative 4. For 49, 7 and negative 7. For negative 4, negative 4 has no real square roots. Okay? So now let's move on and talk about both the positive and negative square roots. We just identified them. Okay? So if I'm taking the square root of a, okay, that means I'm looking for the positive square root of a. And the positive square root is also called the principal square root. If I'm looking for a negative square root of a, it's going to have a negative in front of that radical sign. So if I'm looking for the positive, it's just an implied positive, okay, implied. And then the square root of 0 is just always 0. All right. So if I'm looking for the square root of 25, then that is going to be 5. The square root of 0.81 is 0.9. Now, because there is a negative in front of that square root of 36, that means I'm looking for the negative root. It would be a negative 6. The square root of 4/25 is going to be 2/5. Because I have the negative in front of the 1/9, the square root of negative 1/9 is just going to be a negative 1/3. Now, for this next one, the square root of negative 4, there is no square root. The square root of 1 is 1. Square root of 0 is 0. Okay, you're with me. So now let's up it a level and talk about the definition of an nth root. So that means instead of just talking about a square root, we could talk about any root. So we have to understand what the terminology is. So if I kind of blow up this radical, so this sign right there, that symbol, that is called our radical. Inside that check mark, that is where our index lies. Underneath that radical is what we refer to as the radicand. It can be an individual number. It can be a variable. It can be some combination. It can be an expression. A radicand can be almost anything. All we know is it's underneath that radical symbol. Okay. So, here we go. Let's look at evaluating a radical, the nth root of a. So we don't know what n is. But here's some things we do know. If n is even, okay, then that is going to give us a principal positive nth root. So like the square root of 4 is 2. If n is odd, then the nth root is going to be the root of a. So it's going to be, in this case, the cube root of -8 is -2. If n is an integer, then the nth root of 0 is just 0. All right, so now let's evaluate. So the cube root of -64, we need to think about this. So that means if I could take -64 and find a base that I can raise to the third power, so -4 raised to the third power gives me -64. So that means that the cube root of -64 is equal to -4. That makes sense because our nth root is odd. And so it makes sense that we could have a negative root. Okay, for B, our nth root is even. And so I want to find what number can I raise to the fourth power that's going to equal 256. Okay, and that is going to be 4. 4 raised to the fourth power is 256. If you are unsure about that, just put it in your calculator, like I showed you on an earlier video. All right, let's go to C. So I have an odd nth root, and so it's okay to have a root that is negative. And so if I try to find the cube root of -1/8, that would simply be -1/2. -1/2 raised to the third power is going to give me -1/8. Now I have an even nth root, and so that is going, or an even index, and so that means that I cannot have a negative underneath my radical sign. And so this would be no real solution. Okay, let's go on and look at roots of variables. This is a little bit more interesting instead of just looking at roots of numbers, just because a variable represents an unknown. Okay, so if I'm evaluating the nth root of a to the n power, then if n is odd, okay, if that is odd, then my answer has to be, my root has to be equal to that base. If n is even, Okay, so if my index is even, then in order to make sure that I have a positive root, I would need to use absolute value signs. Because remember, for evens, you could have, when you put this in exponential form underneath that radical, you could have two negative numbers that could be multiplied together to get that product, or you could have two positive numbers. All right, so we don't know whether we're talking about a negative or a positive, so we use absolute value signs to ensure that our answer is always positive, because that's what we want. So let's see how that works. So here I have an odd index. And so absolute value bars are not necessary, because it doesn't matter what y is, it could be negative. Now, if we have an even index, okay, well, we need to be able to use absolute values to show that our root is truly even, that it's not a -3 that we're concerned with, but we want it to be a +3. All right, so again, we have an even index. So we put absolute value signs around that base, and that the absolute value of -2 is 2. And then we're not sure the value of x, and so we keep the absolute value signs around it. Okay. All right. Again, for this last one, we have even, but our base is x squared. So the -2, we need to have absolute value, evaluate the absolute value of -2, which is +2. But x squared is always going to be positive. So we can actually throw away the absolute value signs when our variable is squared. All right, so let's see how we would simplify these expressions, when we would need to use absolute value signs and when we don't. So we only need absolute value signs, okay, around our root if the index is even. So I see that I have an odd index, and so I'm not going to need absolute value. And so my root is simply going to be that x plus 8. What basically is happening, and we're going to work on this a little bit more, is the 5 and the 5. You can think of it as canceling them out. That's not what's happening mathematically, but if you think of it that way in order to pull out your base, that's okay. All right, for this next one, we've got a negative on the outside, and we have an even index. All right, so we're going to pull out an x plus 1 as our base, but because it's an even index, we need the absolute values, and then we put the negative on the outside. Okay, for number 6, our base is x squared plus 7. Because of that, x squared doesn't matter that we have an even index, okay? Because the x is squared, it's always going to be positive. So we do not need the absolute value signs. For number 7, I can rewrite this as -5th root of -2 to the 5th. -2 to the 5th gives me -32. But because my index is odd, I do not need absolute values. This is going to be the negative of that base, -2, which is a +2. 2. For number 6, I have an even index, okay? And so that is going to simply give me 5x, and that is going to need absolute values. Now, I can take the absolute value of the 5, which is 5. So I get 5 absolute value x. For 7, a huge index, 58. But I notice that it's even. So this is going to be the absolute value of x plus 8 over 3. The absolute values only need to go over the part that has the variable, so the x plus 8. Okay, now for the let's move on. And a very common application of radicals is going to be with the Pythagorean theorem. That's where we have a squared plus b squared equals c squared. A lot of people are super familiar with this, so let me just kind of refresh your memory. So the legs come together to form that right angle. That's what's happening here. And you can call either one A or B, doesn't matter. But what does matter is the C is always the hypotenuse. And the hypotenuse is always directly across from that right angle that is formed by the A and the B. Okay, so in this example here, we have a triangle. The 15 is that hypotenuse, and so that's our C value. And then the 9 is one of the legs that is coming together to meet that B, okay? So I'm going to call that A. So then we just plug our numbers in. 9 squared plus B squared is equal to 15 squared. Solve for B. So right here I get B squared is equal to 144. Well, I'm not looking for B squared. I am looking for just plain old B. So the way to find plain old B is I can take the square root of 144, which is then 12. Okay? All right. So let's see what this looks like in just a regular story problem. So we've got a store that has a ramp to its front door to accommodate the handicapped. If the distance from the door to the end of the ramp is 25 feet, so we're talking about this base, that's 25 feet. And the height from the ground to the front door is 7 feet. So right here, that's 7 feet. So what we want to know is the length of that ramp. That ramp is our hypotenuse. So if we set this up as using a squared plus b squared equals c squared, that's going to be 7 squared plus 25 squared is equal to c squared. Or, let me get back here. 49 plus 625 is equal to c squared. Add those together, and I'm going to have 674 equal to c squared. Well, I'm going to have to put that into my calculator because c then is the square root of 674, which is approximately 25.96 feet. Well, nobody's going to measure it in 25.96 feet. So we would say that is approximately 26 feet. Okay. That's how long that ramp is. All right, let's look at this next example. On a sunny day, a building and its shadow form the sides of a right angle. Okay, so we've got the picture there that shows the building, shows the sun, okay, and we can see our right angle. So the hypotenuse is 37 meters long, and the shadow is 21 meters. How tall is that building? Okay. And it's telling us to round our answers to the nearest tenth of a meter. So we're going to set it up as height. I'm going to call that question mark on my height. So height squared plus 21 squared equals 37 squared. So that'd be height squared equals plus 441 is equal to 1369. So when I subtract 441, I get height squared is equal to 928. If I take the square root of 928, then that is about 30.46. It says to round to the nearest tenth of a meter. Well, that 4 is in the 10th position for place value. So I look to the 6 to make a decision. 6 is larger than 5, so I round up. So this is approximately 30.5 meters. There we go. Now let's look at this last one here, this last story problem. On a sunny day, a tree and its shadow form the sides of a right triangle. If the hypotenuse is 50, okay, so there's our hypotenuse, and the tree is 40 meters. Okay, how tall or how long is the shadow? That's what we want to know. All right, so we would set that up as 40 squared plus, I'm going to say B, our base, squared, equals 50 squared. So that's going to be 1600 plus B squared is equal to 2500. Subtract 1600, so B squared is equal to 900. The square root of 900 is going to be 30. That is what that base is, or that shadow. That's the length of the shadow. All right, let's look at radical functions. So I've got a function, f of x is equal to the nth root of x. That's a radical function, okay? So if we're given a function, f of x is equal to the square root of 3x plus 7 for x equals 6. All I do is I plug 6 in where that x is. When I put it here with the f, all that is saying, it's asking the question, if x equals 6, what is y? That's the question. Okay? So underneath your radical sign, you have 18 plus 7, which is 25. And so the square root of 25 is 5. So that means if x is 6, y is 5. Let's evaluate 2 more. So let's look at the f of 7. So this one is going to be the square root of 5 times 7 plus 1. So that's going to be the square root of 36, which is 6. So that means f of 7 is equal to 6. Let's evaluate this last one. G of 4. So I do G of 4 because it's telling us x equals 4. What I want to know is what is G of 4 or what is y? Okay, so that's going to be the square root of 3 times 4 squared plus 16. So that's going to be the square root of 3 times 16 plus 16. Oof. Well, that's going to be 3 times 16 is 48, plus another 16 is going to take us up to 64. So that'll be the square root of 64, which is 8. There we go. All right. So now we know how to evaluate. Now we need to determine the domain. We've already done this. We did this earlier, okay? So we'll just do it again. If n is even, so if our index is even, then the function is going to be a real number only if the radicand is 0 or positive. Therefore, what you need to do to find the domain, you need to set the radicand, create an inequality greater than or equal to 0. If n is odd, then the domain is automatically all real numbers. Okay. All right. So let's see how that works. Let's just go down to 13. Okay. You can look at those examples on your own. So for 13a, I'm going to take 3 minus x and create an inequality greater than or equal to 0. So I'm going to go ahead, subtract 3 from both sides, so I get negative x is greater than or equal to negative 3. I am going to divide by negative 1. When I divide an inequality or multiply an inequality by a negative, it changes the direction of your inequality. So this is now going to be x is less than or equal to positive 3. All right, so to write that domain in interval notation, okay, so it's all of the numbers, here's 3, and 3 is included. It's all of them smaller. So that is going to be negative infinity to positive 3 square bracket. Okay. So for B, I have an odd index. So right away, I know that I don't have to worry about restrictions on the domain. That my domain is going to be negative infinity to positive infinity. Now for G. For G, if I take x squared plus 2 is greater than or equal to 0, okay, because it's an even index. If you think about that, there is no number that x can be that is going to create this or make that value to be negative. It's always going to be positive. And so there are no restrictions, and our domain is negative infinity to positive infinity. All right, let's go to 14. So for 14, the first thing it's asking us to do is to write the domain in interval notation. So I'm going to go ahead, and that is, I see that it's an even index, so I'm going to write it as 5 minus x greater than or equal to 0. And so then I'm going to subtract 5, so I get negative x is greater than or equal to negative 5. I'm going to divide by negative 1, so I get x is less than or equal to 5. Okay. So in interval notation, so if I was to sketch that out, I've got 5, and everything to the left of 5 would be part of my domain. So that's going to be negative infinity, comma, 5 square bracket. Infinity always has parentheses. So that's why we write it like that. Now we're going to graph this just by making a table of ordered pairs. Well, I know that it's going to go to the left, okay? And so I'm just going to pick, let's just pick negative 4, 1, 4, and 5. And so if I plug those numbers in, because my domain can be anything that's less, that's what it says. My domain can be anything less than 5, but can also include 5. So that's why I picked those X values. When I plug in a -4, I'm going to get the square root of 5 minus -4, which is the square root of 9, which is 3. So I get -4, 3. Let's plot it. -4, 3. There it is. Now let's plot 1. Okay, so it's going to be 5 minus 1, which is going to be the square root of 4, which is 2. So we'll plot that. 1, 2. There we go. Now let's plot, or let's go ahead and put 4 in. So 5 minus 4, the square root of 1, which is 1. So if we plot 4, 1, there we go. Now let's see what happens when we put 5 in. It'll be the square root of 5 minus 5, which is the square root of 0, which is 0. That's going to be right on the x-axis. And so that is a sketch. It's kind of backwards here. Our sketch looks like that and goes on. There we go. Wow. Let's do 15. So for 15, we're looking at a cube root of x plus 2. Okay. So our domain, because we have an odd index, our domain is all real numbers. So -infinity to +infinity. We don't have to do any calculations. That's just what it's going to be. And so for our graph, let's just go ahead. We can pick whatever we want. So I'm going to pick 6, -1, -10, -2. So I just pick numbers that I know are easy to work with. So I'm going to go ahead and look for the cube root of 6 plus 2, which is the cube root of 8, which is 2. So I'm going to go ahead and plot 6, 2. There we go. Now I'm going to go ahead, plug in a -1. So that's going to be, for x, -1 plus 2, which is going to be the cube root of 1, which is 1. So -1, 1. There we go. And now I'm going to put in -10. So the cube root of -10 plus 2, that takes us to the cube root of -8, which is a -2. So -10, -2, oh, I don't know, here's -10 somewhere out here, and -2 right around there. Okay, if we kept going with that. There we go. And then lastly, let's go ahead and put in -2 plus 2, which is the cube root of 0, which is 0. So -2, 0. All right. So this one is just going to be kind of a little bit of a sideways S-curve, just like that. It's just so beautiful. And that's what that looks like. All right. And you can check those. You can always check them on your graph. So you should now have enough information to do your homework and have fun with it.